Okay, Bismillah ar-Rahman ar-Rahim. Today I'll present the heat integration, where it is an essential part for the process design to add a conceptual process design that will save a lot of resources that will improve the profitability of the plant. So today I will discuss how we can add more integration, more elemental and important aspects of savings to chemical processes. So at the beginning, the question comes, why we are integrating heat? Can you see the screen? Can you see the
Yes.
presentation?
Yes, we can.
Okay.
Yes, we can see it.
Why
Yes.
do we integrate heat? Okay, why do we integrate heat? First of all, the heat is in the process. Either we have process streams to be heated or cooled, and those process streams that needs to be heated or cooled, they need utilities in the plant in order to heat them or cool them. Yet we have energy contents in those process streams. So the question comes to any process engineer, why we don't save utilities by utilizing those process streams. The heat comes from those process streams. So the energy or the heat is provided in the process by what? By utilities. And these utilities can be hot utilities or cooling utilities. For example, in order to heat streams, we need steam to do that. And in order to cool streams, we need cooling water in order to do that. Those utilities that you usually use, they are of a high cost. So how do we save them? This is the challenge. How do we save these utilities? They cost a lot in the plant. The question is, how do we save them? So in this presentation, I'll show you methods that will help you to do that. And at the beginning, I wanted to share with you the onion process design diagram, the onion diagram, the famous one, where we, as a traditional process design, usually we start with the reactor. First of all, we start in the design in the reactor. Then we go to the separation, the separators or distillation columns or fractionation, extraction, whatever. Then after that, we go to the heat exchanger network. What is the heat exchanger network? The heat exchanger network simply, it is the collection of the heat exchangers in the process. So if you have, for example, in the PDH process, let's say you have 20 or 30 heat exchangers, those heat exchangers are called heat exchanger network. All these exchangers, they are connects to each other, or they connects to utilities, or they connects to the process. So they are one network, and this is where we recover heat. Then after development of the heat exchanger network, we will now use the utilities in order to provide the needed cooling or heating. We'll utilize and use utilities. For example, here in this process, how many heat exchangers do I have? I have two that utilize steam for heating. I have two that uses cooling water for cooling these streams. So all the requirements for the heating, which is about 15 megawatt, comes from steam, while the needed cooling water duties for those heat exchanger, which is about 61.5 megawatts, come from the cooling water. So both the steam and cooling water are the utilities for these heat exchangers. Now the opportunities come, the opportunity comes here. Can we save energy in these processes? Yes or no? Yes. We can exchange heat by feed to for example, the product two and product one with the feed one, okay? Or the, sorry, this stream with the feed one. We can exchange, instead of having a utility heat exchanger, we can have a process to process heat exchanger. And that will save utilities. Instead of spending 59 megawatt, we may need much less than that. Instead of spending 61.5 megawatts for cooling, we may need less than that if we integrate these streams, the hot stream and the cold streams. The analogy of defining the hot stream or the cold stream is as follows. The streams that need to be cooled are cold. The streams that need to be cooled are called hot streams. And the streams that need to be heated are called cold streams, regardless of their temperature. We just look at why or what do we do with that stream? Do we heat it or cool it? If we are heating it, then that's called cold stream. If we are cooling it, then that is called hot stream. So let's integrate the heat and see if we get better utilities requirements, if we have less utilities requirements. If we integrate this system, we will get the following network, okay? We will get the following network, okay? Which is very interesting. This is complicated, I'll come to it later on, but we're able to reduce the heat or the utilities by 85%. In order to reach this scenario, let's define some basic definitions. So first basic definition here is the heat exchanger network design. Usually we design it, this heat exchanger, taking in consideration the process stream's heat content, energy content, that will help us to reduce the cooling and heating requirements. And in order to do that, we must know also the LMTD, logarithmic mean temperature difference. We must know LMTD. Q, the heat duty for that heat exchanger, equals to UA LMTD. U is the overall heat transfer coefficient. Okay. While A is the area of the heat exchanger, and LMTD is the logarithmic mean temperature difference. So as you recall, Q here equals to UA times LMTD. Okay. U is the overall heat transfer coefficient where it will consider all the resistances due to the conduction, convection. Area of the heat exchanger, LMTD logarithmic mean temperature difference. We can find it for co-current or counter-current heat exchangers. Also, another definition, we must also define the driving force, which is delta T min. Delta T min is the driving force, the minimum temperature difference, which is the difference between the hot stream entering and the exiting cold stream, or the exiting hot stream and entering cold stream. The minimum among them, we call it ish, the delta T min. So for this is the heat exchanger, the counter current heat exchanger, delta T min is 20. While for this heat exchanger, the delta T min is 10 degrees. We have a 2010, the delta T min is 10 degrees. So delta T min is the minimum temperature difference, and it is considered as a design parameter also for the heat exchanger network that we are designing. And the delta T min can be obtained considering the cost, the capital cost and operating cost. The duty, another definition also to consider it here is the duty of the heat exchanger. The duty is UA LMTD as explained to you. This is the duty of the heat exchanger. Okay, so for example, in this heat exchanger, Q equal to UA LMTD, okay, or also MCP delta T, as you have discussed or studied in the CHE 202 in the energy balance course. We studied that also Q is MCP delta T. So Q here is also MCP times delta T for that stream. So for this cold, for example, cold stream, it enters at 40, exit at 70, so delta T is 30. And MCP here is the mass of that stream, mass flow rate times the heat capacity. We can write this as well as capital C, capital P. This is called heat capacity flow rate. Heat capacity flow rate. Okay. So for example, this hot stream is 0.3. So its duty will be what? Will be 0.3 times اللي هو heat capacity rate times the delta T, which is 40, which gives us 12 megawatt. For this cold stream, it is 0.4 times 30, which is still also 12 megawatt. So the heat that is donated by the donor, the hot stream, goes to the cold stream. So the cold stream is heated by that hot stream. Okay. Where the supply temperature for the hot is 100, the target temperature is 80. For the cold, the supply temperature is 40, the target temperature is 70. So this heat exchanger will exchange 12 megawatts, will be heating energy that comes from the hot stream to the cold stream, which is 12 megawatts. So 12 will be rejected by the cold stream, and it is donated by the hot stream. And there are two types of the heat exchangers. There is a process-to-process heat exchanger, and there is also utilities heat exchanger. So we have two types. The first type, process-to-process heat exchangers, means all the hot streams or cold streams in the heat exchanger are coming from the process streams. So they are either products, maybe feed, maybe intermediates, but all of them, they are related to the process, they come from process. And we have utilities heat exchangers where the heating and cooling requirements, they come from the utilities, which can be cooling water, refrigerants, etc. for the cooling. They can be hot oil, steam, low pressure, high pressure, very high pressure, whatever, medium, high pressure, medium pressure steams, etc. for the heating utilities. Now the question, how do we utilize the heat in the process streams to save energy? This is the key question here, why I'm presenting for you this lecture. So let's go to the example I showed you before. This example, how many heat exchangers do we need? Can anybody answer to me? How many heat exchangers do we need in this example?
4.
We need 4 heat exchangers. How many for cooling?
2.
2. We need these streams to be cooled. Okay, this is cooling. This is for cooling. How many heat exchangers for heating? 2 for heating. We need hot utilities here. We need cooling utilities. This is the traditional way. How do we do it? So if we are doing it the traditional way, we will design 4 heat exchangers. All of them are utilities exchangers or process-to-process heat exchangers. What is the type of these heat exchangers?
Utilities heat exchangers.
All of them, they are utilities heat exchangers. Do we have opportunity to save energy here? Yes. How? How do we save energy?
By exchanging heat.
Yes, by exchanging heat from where to where? Can anybody give me just one scenario that will save energy? One scenario.
Connect the cooling with the heating.
Yes, which cooling? Which stream with which stream? Hi, Shabab.
Outlet of reactor 2 would be the heating of the heat exchanger in feed 1.
So we can take the output from reactor 1, which needs to be cooled. We can take this hot, exchange heat مثلا مع this stream that need to be cooled. This is one idea. Yeah. This is one idea. And instead of using utilities, we can use this steam instead, isn't it? We can also use, for example, this stream, okay? We can take it now, the same stream, and use it for example, heating this stream. This is another idea. So let's see the optimum way. If we do the design, if we do the most possible saving, let's see the new design. Okay. Let's see the new design here. This is the most efficient design. What do you observe here? First observation. Can somebody give me first observation?
Heat exchangers are more.
Heat exchangers are more. Excellent. This is excellent observation. Any other observation?
This amount,
duties are less.
Duties are less, much less. Before, we have 59 megawatts for cooling, 61.5 megawatts for cooling, and 59 megawatts for heating. Now we have for the heating how much? 7.5. For cooling, we have 10 megawatts. So the saving of the cooling utilities and the heating utilities is 85%. Do you think that worth it to do this way of heat integration to save 85% of the cost? Do you think does it worth it?
Of course.
Of course, 85%. So if you are spending, for example, $1 million per year for these utilities, how much you will pay now?
150.
Integration. Now?
150,000.
150,000. Big saving. If you can achieve it, that would be great. So this is the new design. Now the question, how do we achieve to the scenario? In order to do that, we need to construct the pinch analysis. What is the pinch analysis? First, we need to construct the cold stream curve. We combine them in one curve. Then we combine the hot stream in one curve. Then we put them in one composite curve. Then we pinch them in the pinch diagram. This is the way to do it. How do we do this? First, we need to set up the energy target. What is the energy target? The minimum cooling and heating utilities requirement. This is what does it mean. Okay. So how do we do this? We do this by the pinch analysis, pinch technology. We usually do this. We construct the pinch diagram, we find the pinch point, pinch temperatures, minimum heating utilities, minimum cooling utilities. Once we set the target, the energy target, which is the minimum utilities requirements after the integration, we can go and develop the design, the excellent design of the process. Okay. So let's see how do you construct the pinch diagram. For example, for this two heat exchanger example, where I have a hot stream to be cooled and a cold stream to be heated. So how do I construct the pinch diagram? First, we need to tabulate them. How do we tabulate them? We write the supply temperature, target temperature for all of them. Then we also need to find the heat capacity flow rate. And of course, after that, you can get the duty. Or you have the duty and you get the heat capacity flow rate, either way. You need to tabulate only the process streams in the table. Then after that, we plot them on TH diagram. We plot them on the TH diagram. So the current situation that the hot stream is cooled from 160 to 40, while the cold stream is heated from 40 to 110. The hot stream is cooled currently by all from the cooling water with a duty of 12 megawatts, and that is the situation. All the duty comes from where here? Comes from the cooling water. And for the hot stream, for the cold stream, it's heated from 40 to 110 with a duty of 14 megawatts. All the requirements for the heating comes from steam, and that is the current situation for this cold stream. All the heating comes from the steam, from the utilities. Can we save energy here? Yes. we can exchange the hot coming from the reactor with the cold comes to the reactor. Okay, so we can integrate the streams. How do we integrate them? We need to set up first the delta T min, the design parameter. So let's say delta T min is 10 degrees. If it is 10 degrees, what do we need to do? Shift the cold stream curve into the hot stream till you reach the shortest vertical distance to be not more than 10 degrees. After doing so, the overlap between those streams, the heating requirements and cooling requirements come from the two processes exchanging to each other. While the hot stream here, the remaining the hot stream here, the cooling comes from the cooling water. The heating here comes from the steam. So theoretically, how many heat exchangers do I need? The minimum number of heat exchangers theoretically here.
3.
3. I have one process to process and 2 utilities heat exchangers. This is a process to process, and that is utilities. For the process to process, I need 11 megawatts as a duty for this heat exchanger, where I just use the heating and cooling from the process to process heat exchange. This heat exchangers I only need 3 megawatts for the heating, and here for the cooling I need only 1 megawatts. Yet I added one heat exchanger, but how do you observe also? I added one heat exchanger, yeah, I added a capital cost. However, on the contrary, what do you observe? Yes, any idea? Yes, Shabab, any idea? What do you observe also? Yes, reduction in the operating cost. Excellent. Okay, Hussein, reduction in the operating cost. Okay, reduction in the operating. How? Because I was able to reduce the cooling water utilities and the steam utilities. If the delta T min is 30 degrees, do you think the operating cost will be less or high? It will be higher because I increase the driving force. So the integration will be less and the utilities, the operating cost will be higher. Okay. Let's take now to a process, actual process. Let's see how do we reduce it? How do we reduce the energy? So I have here 2 hot streams and 2 cold streams. Currently, I'm using only utilities for the heating and cooling. Is there any opportunity for saving? Yes,
Yes.
no? Yes, definitely yes. I can have those streams to exchange heat to each other. So currently, I need 83 megawatts for cooling, 56 megawatts for heating. After tabulation, first you need to tabulate all the streams from supply to target with heat capacity flow rate, find the enthalpy. This is currently the situation. Can I reduce it more? I need to find the energy target. See the new energy target, what it will be. So we need to set the energy target. If we have the exchange only between the hot streams and the cold streams, what will be the new energy target? How much of utilities? And based on that, I can say that I'll save less or more. Okay, maybe my process is already integrated, maybe not. For this case, it is obvious it's not integrated. Maybe other processes, it is already integrated or it has a lot of integration. So generally, first step is to set the energy target. How do we set the energy target? By using the pinch analysis, pinch technology. Okay. So in order to do that, you can do this graphically. This is the usual way is to go set up a graph and do it graphically. But due to the limitation of your situation, since you have a senior design project, we will do that in the Excel. Okay, we will do that in the Excel program. So I'll show for you now Excel separate sheet. Usually we do it, we use it for the integration. However, first of all, your job is to tabulate the hot streams and cold streams into it. This is your job. So let's see this screen and how do we do it. Okay. Can you see the Excel sheet, Shabab?
Yes.
Yes, we can.
So this Excel spreadsheet is very interesting. First of all, it is a pinch analysis spreadsheet. It will save a lot of your time once you are using it. So in order to use it, first you need to input the data. So you go to the input here. You first choose the method you want to use. Will you provide heat duty, or you will provide the heat capacity flow rate? It depends on what you have. Maybe the heat exchangers you have the duty instead of the heat capacity flow rate. Then after that, you need to provide the minimum delta T min. What is delta T min? You need to provide delta T min. 10 degrees Celsius or 10 degrees Kelvin, which is the same. Okay.
Doctor,
Yes.
do we assume this value?
Usually it is calculated from the process. Okay, you need to calculate the effect on delta T min on the operating cost and the effect on delta T min on the capital cost. Then you plot the total annual cost, the minimum associated to the minimum temperature difference. Okay. But usually it is for petroleum refining, we are talking about 25 degrees Celsius. For petrochemical processes, as you have in the PDH process, usually it is from 10 to 15 degrees Celsius. But it can be less, it can be more. You need to calculate that if you want a precise value. Okay? So let's go now to this example. After that, you need to check which unit you are using. Are you using SI units, metric, okay, US units, whatever you are using, you need to put that. Then you put all the data. I already entered the data, but you need to do it yourself. You need to enter all the data. So here in the data, as I showed you here, these are the data. This is supply temperature, target temperature. This is CP, this is the duty. You can choose the CPs or you can use the duty. Either one will work. Can you see the slide? Yes.
Yeah.
No. Okay. Now we'll go to the separate sheet, back to the separate sheet. So I put all the data. I put now the heat capacity flow rate in there. So I'm ready to go to the pinch diagram. So the pinch diagram, the composite curve is in here. This is the composite curve. Where is the pinch point? The pinch point is here. Okay. What is the minimum cooling and minimum heating? I need to go to PT sheet, and it will show to me the pinch temperature for the hot and for the cold. It will show to me also the minimum heating utilities and minimum cooling utilities requirements. So now I need 33 megawatts and 60 megawatts for heating and cooling utilities requirements respectively. That is with respect to $83 and $56 megawatts for cooling and heating utilities. Do you think there is a saving? If we compare, for example, the heating, we need 56. That's for the heating, 56 megawatts. Now I need only 33 megawatts. And the cooling is 83 megawatts. Now I need only 60 megawatts. So the new energy target considers the saving of the utilities if we integrate the streams with each other. So if we integrate the stream with each other, then this is what we will get. 33 megawatts as a heating and 60 megawatts for cooling. Okay. So this process will, this separate sheet will show you the composite curve. It will show you also the target values for the minimum heating, minimum cooling, hot pinch, cold pinch. It will also show to you the delta T min, how delta T min it will change with the temperature. So here, if we change delta T min from 10 to 30, we can also show, we can see how this will change in the separate sheet. Okay. So back to the slides. So these, the new savings, if delta T minus 10 degrees, we are saving 41% of the heating utility and 28% of the cooling utility. Okay. And that's give you a good exercise. How do we consider integration in the process? And how do we also check the energy target and see our process, does it hold, can be integrated more or not? And usually most of the conventional processes, most of them, especially the old ones, they have a lot of opportunity for energy integration or energy optimization or heat integration. So that is the end of the lecture. I hope you enjoyed it, and it will add a lot. For the PDH process, you can do the same. You can just go there for the PDH. If you have just plot, find the PFD. By now you have the PFD. Check the heat exchangers that you have. See the set up the target. Put all the streams, the cold streams and the hot streams in here, regardless of the utilities. Don't put utilities in here. Just the hot streams, the process, hot stream and cold streams, tabulate them. Use the separate sheet to target the energy and modify your design to reach that savings, or maybe not exactly the same numbers, or that you got maybe less than that, but definitely you will have an integrated process that will save energy for you. Okay, that's summarize what I want to say in this lecture.